we're happy to have the first inauguration lecture, Bott lecture, from CMSA, Center of Math Physics, Center of Math Science. And well, Raoul Bott was our faculty here, one of the greatest topologists and geometers in the last century, and we are proud to have him here. And we are very glad that Cliff, student, Casper Ernst, donated money for this great lecture. And of course, we like to honor Cliff, but he refused, so we give it. So we are honoring Raoul, which of course we all admire, so there's no question we like to do that. So this lecture series will be today and tomorrow, of course, but also each year we would have a lecture given by distinguished mathematicians, probably in different fields. Cliff will be in charge of such a lecture. So Cliff will be chair.
Well, I want you to do first, introduce our speaker, and then, but first, before I do that, I just wanted to again, publicly thank my ex-student Casper Ernst, who donated money for the lecture series, and so Casper couldn't come, but he sends his best wishes, and I think. At least, silently, we should all thank Casper for the for endowing the lecture series in honor of Raoul Bott. And okay, so now our speaker, the first speaker in the first lecture series is Freddy Cachazo, who's the Gluskin Chef Freeman Dyson Chair in Theoretical Physics at the Perimeter Institute. In Canada, and he's known for his contributions to quantum field theory via new approaches to computing scattering amplitudes, and these discoveries have revolutionized computations of particle scattering, calculations that people previously couldn't imagine doing, and now they can do. Some of them are directly relevant to experiments, but on the other hand, the mathematics that he's uncovering is beautiful mathematics that's related to sort of topical research in geometry and algebraic geometry. So combinatorics, it's really remarkable. Freddie graduated from Simon Bolivar University in 1996. He actually got his physics PhD here at Harvard, so this is coming home. He received lots of awards, Griboff Medal in 2009, the Rutherford Medal in 2011, Herzberg Medal in 2012, and then he was a recipient of the New Horizons Prize in 2014, and then in 2016 the Canadian Association of Physics Prize in Theoretical and Mathematical Physics. With that distinguished pedigree, we're glad to have him tell us about these new discoveries.
Okay. Well, thank you very much, Cliff, for the nice introduction. And as he said, it's a pleasure to be back home. It's always great to be back at Harvard, and especially to inaugurate this series of lectures. So today I'm going to tell you about unexpected geometric and combinatoric structures in particle interactions. That title was too long, so I had to settle for something smaller. So that's why it's just geometry and combinatorics in particle interactions. So I'm going to tell you today, let me see. Probably have to twist this. Does it work now? Okay, I was going to move on to the outline of the talk. So in these talks, I'm going to give you 3 approaches to solve a given problem. The first approach is going to be the standard approach. All right. Let me try. Oh, it might be frozen. Why is it not working? Okay. Let me see. Could go back. Okay. All right. So as I was saying, this is the outline of my talk, or my series of lectures. So I'm going to give you 3 approaches to solving a problem. First, we're going to discuss the standard approach. Of course, in giving you the standard approach, I will also give you the definition of the problem that we want to solve. Then we're going to move on to the combinatorial approach. And last, the geometric approach, which is going to happen tomorrow. Okay? Very good. So let's start with the definition of the problem, or the standard approach. Imagine that you're given a particle collider. Okay? Yes, after some billions of dollars, you're giving a particle collider. So you're given the Large Hadron Collider at CERN. This is nothing but a 27-kilometer ring where you accelerate protons almost at the speed of light and you make them collide. So you have billions of protons colliding per second, and you get beautiful pictures like this. What are these pictures? Well, every ray that you see here is a particle, and now your job is to compute the relative frequency of the resulting events. So how do you even start to approach such a problem? Okay. So you have to understand or devise a mathematical framework to understand the particle interactions in nature. And that framework is what we know as quantum field theory. So let me just tell you what quantum field theory is by telling you the meaning of each of the words in the name. So what is a field? In its simplest form, is a map from space-time, which we take to be R3,1 into the reals. What is a theory? A theory is described by the choice of what is known as a Lagrangian, which is nothing but a function of the fields and its derivatives. And with a Lagrangian, we integrate over space-time to produce what is called an action functional, which is a map from the space of fields into the reals. If you were considering just the critical points of this functional, you would be doing classical field theory, but that's not what we're interested in. We're interested in quantum field theory, and that's why we have to do this very complicated and often, or most of the time, ill-defined object, which is a path integral or a functional integral over the space of fields. Now, in order to get the predictions that we need for our experiment, it's not this path integral that we have to do, but we have to do something slightly more complicated. This is what we have to do. We have to perform this integral with insertions of the fields at different space-time points. And from these objects, which look pretty much like statistical physics objects, we construct something that is called the Green's function. And from here, we are supposed to extract the physical data. And how do we do that? Well, the next step is to take the Fourier transform of this object in order to construct something that depends on the dual space to space-time. The dual space, in the sense of a vector space, is called momentum space. Now, for each point, we have associated a momentum, PA. And these momenta are the data that experimentalists will give us or that they will measure. For these are the properties of the particles that we are interested in. Now, it turns out that this complicated object has poles, and the poles are located where the norm of these momenta happen to coincide with a property intrinsic to the particles, which is called its mass. So every time the momentum of one of the particles approaches its mass, this object blows up. It has a pole, and we can perform an expansion in terms of these singularities. And the term that is the most singular, meaning that it has all possible poles for all particles, is the object we're going to be interested in. Here we have less singular terms, and sitting at the pole when the momentum squared of a particle is equal to its mass is what we call to be on-shell. So this is an on-shell expansion of this complicated object. And this is the object we're interested in, and it's called the scattering amplitude. All right, so let's summarize what we have done so far. So a scattering amplitude from now on will be denoted by this blob with lines coming out. Each of the lines represents a particle. and in mathematical terms, is a multidimensional residue of a function obtained from the quantum fields. It encodes all the physical information we need to make predictions. These predictions about the relative frequency of the events that we see at these colliders is all encoded in these objects. Now, how do we compute these scattering amplitudes? That seems like a very complicated task, and in fact it was, until Richard Feynman came out with a very simple tool for computing these objects. And these are the famous Feynman diagrams. So Richard Feynman introduced this diagrammatic approach, and let's take, for example, the case when 5 particles interact. You have an expansion in terms of diagrams. Now note that here on purpose, there are 2 different kinds of lines. There are thin lines and thick lines. What do they mean? Well, the thin lines correspond to particles, these objects that we see on the experiments, that we see on the detectors. The thick lines correspond to objects built out of fields that we don't detect. We never see these things, but they come in the expansion that Feynman derived. Now, for 5 particles, this seems a simple game of using the rules and putting them together to find out what the answer is. And indeed, it's a simple rule that we can just teach a computer to do and give us the answer. So here is part of the answer. So this is part of the answer for this process of 5 particles. As you can see, well, hopefully you cannot see, and that's the idea. And here is a zoom out part of the answer. So even by following simple rules, we can produce for a small number of particles incredibly complicated answers. So why is this the case? What is the challenge ahead? So this challenge of computing scattering amplitudes comes from the fact that Feynman diagrams are binary ternary rooted trees, or can be related to that. So you have a tree that has a mark point. It can split into 2, or it can split into 3. And each 3-valent vertex in the tree produces 6 terms, while each 4-valent vertex produces 3 terms. So let's just count and see how many terms we have. For 4 particles, we have 4 different trees, 3 of this kind and 1 of this kind. Now we multiply by 6 squared, because we have 2 trivalent vertex, times 3 here, and we get around 100 terms. For 5 particles, we have 25 trees, 15 of this form, 10 of this form. And now you see why, even though it's a simple rule, it can produce an incredible amount of terms. Even for 5 particles, we have more than 3,000 terms. For 6 particles, we have 220 trees, and I didn't bother to count how many terms would that produce, but you can imagine that the numbers will grow astronomically very soon. So it's clear that we need a new approach. Perhaps that's what nature is, and we have to settle for that, or we can try something different. And here we go to the combinatorial approach. Now we have to start with something. So we need some guiding principle that will teach us or will guide us into where to look for. After all, Feynman was a very smart guy. So if we want to find something that allows us to do better, we'll have to come out with a new idea. So what are the questions? The guiding questions. These are the questions. So can scattering amplitudes be computed without using fields? Could it be that all the complication comes from these thick lines? Something that replaces this picture where only thin lines, ones that correspond to particles, appear. And if we succeed in doing that, is there a different combinatorial structure that underlines these purely on-shell diagrams, or these purely on-shell structures? Okay? Now, the start of the whole construction is going to be particles. So if we want to have any chance of understanding what we're going to do, we have to define precisely what a particle is. So in order to give you the mathematical description of a particle, let's start with what is space-time. So space-time, I'm going to take it to be a 4-dimensional flat Lorentzian manifold, and this is the metric that I'm going to take. It's mostly minus. The isometry group is the group that preserves this metric, SO3,1 or SO1,3, is the semi-direct product of SO3,1, which is the generalization of rotations in space, but now to include also time. It's the semi-direct product with an abelian group, which is the group of translations. We have 4 possible directions, so we can translate in any 4 possible directions, okay? The 3 space and 1 time. So our theory has to be invariant under this group, And particles, their mathematical definition is that they are unitary, irreducible representations of this group. Why physicists are obsessed with unitarity, that's part of a different story, so I'm not going to go into that. So just take my word for it, that we have to have unitary reducible representations. So how do we start and construct these unitary reducible representations of this group? Well, there is a standard machinery. The first step is to look at the abelian part of the group. You look at the abelian part of the group, it's just a vector space. Since it's abelian, its irreducible representations are one-dimensional, so it's very easy to construct unitary irreducible representations by just taking elements in the dual space, and these are the momenta that we found before. And that's why these objects appear all over the place. Very good. So before we move on, I have to take a small aside and ask the following question. Maybe you have asked that question yourselves. We know we all love complex manifolds. Now, are complex manifolds just something in our imagination, or is there a complex manifold in nature? Well, that's a question that Roger Penrose asked many, many years ago, and he came with a nice picture to prove that there is a complex manifold in nature. So the picture is the following. Imagine that you step outside on a very clear night and look at the sky. What do you see? Well, you see a sphere that is called the celestial sphere. So this is your eye. You're at a particular time when you look at a particular point in space, and what you see, the stars, the light that you see coming to your eye, is the light that was emitted by stars just at the point when they cross what is called the pass null cone associated to this point. So all these stars were emitting light, but only when they cross this cone, that light goes into your eyes. And what you see, as I said, is a celestial sphere. Okay, but a sphere could just be any regular sphere. Now, what happens if somebody who is on a rocket passes next to you at that precise time, and they also decide to look through the window and see their celestial sphere? It turns out that they will see a different sphere. But we know that the two spheres are supposed to be describing the same physics. So whatever transformation takes one sphere to the other must be a symmetry of the problem. Must be something that identifies as these two spheres. And it turns out that the transformation that relates the sphere that this person sees to the sphere that you saw is an SL2C transformation. I'll tell you later what SL2C is, in case you are not familiar with it, but that's precisely the hallmark of a Riemann sphere. The space of different Riemann spheres is the space of spheres modeled out by SL2C transformations. So our celestial sphere is a CP1. So there is a complex manifold in nature. And SL2C is the double cover of the SO1,3. So I'll take as the Poincare group, not SO1,3, but SL2C semi-direct product with translations. So SL2C is going to be the star of the show. And that's the reason why I had to take this aside. Okay? Now, finally, we are ready to construct the representations we want. And this is the technique of induced representations. And the idea is simply, we constructed the representations of the abelian part of the group. Now we fix a momentum and construct irreducible representations of a simpler problem. The simpler problem is to find the stabilizer of this momentum in SL2C. And the stabilizer, or the structure of this group, depends very strongly on the value of the Lorentz invariant, or the SL2C invariant norm of this vector P, of this object P. If this is greater than 0, we call this number the mass square of the particle. The stabilizer is SU2, and its representations are given by half integer, which are called spin. And all these particles are realized in nature, or at least we believe that all of them are realized in nature. So certainly, we have seen many, many of them. And you can think that even a black hole that spins could be one of them with a very large value of the spin. Recall that this was my choice of the metric. Now, the ones we're interested in for these lectures are actually the ones for which P is a null vector, meaning that its norm is 0, so the mass of the particle is defined to be 0. In this case, the stabilizer is the group of isometries of the plane. So you have rotations and translations on a plane. That's much more interesting than SU2 in the following sense, that we now have, again, to use the theory of induced representations to find these representations. So we find representations of translations, again, by constructing the dual of the space. And if we choose this new momenta, t, this new dual vector, to be 0, then all we have are representations of SO2, and they are classified by an integer, by a half integer, which is called the helicity of the particle. Now, if the momenta is this new momenta is different from 0, then we get infinite dimensional representations, and we haven't seen them. So they don't seem to be there. They are allowed by representation theory, but nobody has seen massless particles with an infinite number of degrees of freedom. So these are the ones we're interested in these lectures, massless particles, which are helicity states. Now, I couldn't resist the temptation of telling you what we have seen in nature. So for the absolute value of the helicity, we have seen helicities a half, 1, and 2, and these are the corresponding particles. Now, Steve Weinberg, in the 60s, already told us a very good reason for why we don't see any of these ones. But there is no reason whatsoever why these one and these ones are not seen in nature. So, who knows? Maybe these are the ones that are waiting to be discovered. All right, so this was also a small aside. But now that we know what are the objects we're looking for, and we want to understand how to construct the scattering amplitude for this object, the next step is to choose the right variables to describe the problem. So what is a choice of variables? So as I promised, I was going to tell you what SL2C was, in case you're not familiar with it. It's a group of special linear transformations in C2. And we can think about G, an element of SL2C, as being represented by a 2 by 2 matrix whose determinant is 1. So special means that the determinant is 1. Now, these 2 by 2 matrices act on a vector space, and the vector space is C2. So we are going to choose as our variables to describe particles elements in C2, but it turns out that we also need elements in another copy of C2 on which the group SL2C acts in its conjugate representation. So we need these two objects, lambdas and lambda tildes. And the massless momentum vector that we had for describing our particles can now be replaced by a 2 by 2 matrix that is obtained simply by multiplying this vector with the other vector. So you get a 2 by 2 matrix whose determinant is equal to 0, so it has rank 1, and that is the object we're going to concentrate on. In fact, we are now ready to tell you what a scattering amplitude is. But before I tell you what it is, let me tell you what it's not. So a scattering amplitude is not a function. How can it be that it's not a function? Well, there is a very simple reason. If you have your experiment, and you perform your experiment here, or you perform it in Jupiter, you should get the same answer, and therefore the amplitude should be translation invariant. But the translation was this part of the group that if you applied it to the particles, they will produce this phase. So all the particles will produce a phase, and therefore invariance requires this equality. But this equality is impossible for a function. So what's the answer? If you are required to have something that behaves like that, it means that it has to have singular support, and it's a distribution. So it's a distribution whose support is precisely the set of momenta that add up to 0. In terms of the 2 by 2 matrices that I introduced before, is given by this object here. So this is an equation for 2 by 2 matrices. So you add up 2 by 2 matrices, and you have to impose that they add up to 0. Okay? So this is the equation that I want you to remember, because it's going to be very important for the rest of the talk. And now we are ready for the first reinterpretation of the data. So far, we have given for each particle an element in C2. So this is a little 2 vector for each one of the particles. So this is a particle label. We go from 1 to n. And we have discussed that the symmetry group that acts on this space, part of it is SL2C. So we have this 2 by m matrix and SL2C acting on it. Well, one way to think about this is to think about each one of the particles and how it transforms under this SL2C group. But another way of thinking about this data is as follows. Instead of thinking about the columns, let's think about the rows. So we have two rows. Each row is a vector in Cn. So we have two vectors in Cn defining a plane. And I'm telling you that if you mix them up, the physics is the same. If you mix them up with an SL2C transformation. So that should start to ring a bell from your courses in algebraic geometry. So the physical data turns out to correspond to points or to elements in the set of two-dimensional linear subspaces of Cn. Well, it turns out that this object has a name. Here I simply said that we can, without loss of generality, expand the group SL2C to GL2C, where we allow the determinant to be different from 1 but not 0. And this is what is known, or this is an example of a space known as a Grassmannian, G2M. So the 2 corresponds to two-dimensional linear subspaces of Cn, and the n tells us the dimensionality of the big vector space. All right? But what we have found here for lambda, remember I told you that for each particle we needed two copies. We needed a lambda and a lambda tilde. So everything that we have done for lambda has to be done for lambda tilde as well. So this is also an element of G2M. And the very important equation that I told you to remember now tells us something about the connection between these two planes, or these two-dimensional subspaces. Now, it turns out, as many of you know, that there is a natural isomorphism between the Grassmannian G2n and the Grassmannian Gn minus 2n, given by saying, well, take the vector space, take the dual vector space, and associate to every two-dimensional subspace the elements in the dual vector space that annihilates it. Okay? That's clearly an n minus 2 plane in Cn. And this equation is simply telling you that this 2 plane, this lambda tilde plane, has to be a linear subspace of the dual of the lambda plane. Okay? Okay, so we have found a reinterpretation of all the data in terms of fancy, well, for a physicist, in terms of fancy mathematics. Okay? For mathematicians, it's probably not that fancy, but for us, it was surprising that these Grassmannians were appearing. Now you would say, well, let's apply this to something. Let's do it for the simplest possible case. Take 3 particles, n equals to 3. Well, I'll give you 2 seconds to do it yourselves, and you find that this whole thing is wrong. It doesn't work. Why it doesn't work? Because I just told you that we're doing it for 3 particles. So fine, this is a 2-plane in C3 in 3 dimensions. But now, this one, which is also supposed to be a 2-plane in 3 dimensions, is supposed to be a linear subspace of G13, which is supposed to be a 1-dimensional space. So we cannot fit a 2-dimensional subspace into a 1-dimensional subspace. So we found a problem. Even in the first case we tried, it doesn't work. So do we get discouraged? Well, maybe. Or we try to move on and see if this is something that was special about 3 particles. And indeed, what is happening is that lambda and lambda tilde cannot both be maximal rank 2 by 3 matrices. So we have to make a choice. It's one or the other, but both cannot be at the same time. So we're going to choose, since we don't have any preference, what we discover is that there must be 2 different kinds of 3-particle amplitudes. So let me call the first one the kind A, where lambda is going to be an element of G23. So it's going to have maximal rank. And instead of using lambda tilde as an honest element of G23, which we know is impossible now, we're going to replace it with a dual of this element of G23, which is an element of G13. These brackets are nothing but the Placard coordinates of this Grassmannian. So you construct these 2, 3 by taking the 2 columns, 2 and 3, and computing its determinant. So here you get 3, 1, you take this and this, you compute this determinant, and 1 and 2, you compute the determinant of the 2 by 2 matrix. And the fact that lambda tilde doesn't have maximal rank means that its columns must satisfy a linear relation, and this is the linear relation they satisfy. Of course, we can reverse everything. Lambda was not more special than lambda tilde, so we can completely go from one side to the other and encounter a different three-particle amplitude. Now, that all sounded complicated, but maybe there is a nicer way of imposing these constraints on these three-particle amplitudes. So the nicer way is the following. So we take, for the first kind, which arbitrarily I'm going to denote as a black vertex with the three particles that are interacting, and the second kind with a white vertex. So what I'm going to do in order to make all that story that I told you before, to write it in a simple form, would be to introduce an element of G23, an arbitrary element of G23, and I'm going to ask this element to coincide with the lambda plane. What do I mean by coinciding with the lambda plane? Well, simply by asking for a GL2 transformation that maps one to the other, so that they correspond to the same two-dimensional subspace of C3. And for the lambda tildes, well, what I ask is this matrix to annihilate lambda tilde. And this means that there are two constraints on this object. Now, in the case B, I'm going to choose, instead, an element of G13, and I'm going to impose two constraints on lambda and one constraint on the lambda tilde. All right. So we're done with our new fancy description of three particles. But we still have 4, 5, 6, and so on. And we only have half an hour left. So it doesn't seem possible, right? Unless something special happens. And the something special that happens is that in 2005, it was discovered that these three particle amplitudes are the building blocks of all amplitudes. Not only 4, 5, and 6, but every single amplitude for any number of particles will be built out of these basic building blocks. So that's the reason there is a chance I can finish this talk on time. And that goes under the name of the on-shell or BCFW recursion relations. Now, it states that amplitudes can be constructed recursively from three particle amplitudes in the following form. You take any amplitude, which is given by the labels 1 through n in any particular order. Here, there is nothing that tells us what order we should choose. And just pick two of these particles, any two. So here I'm picking 1 and 2. And it turns out that the amplitude can be written as a linear combination of the product of amplitudes where 1 and 2 are connected in this form, two lower point amplitudes that correspond to non-empty partitions of the remaining labels. Now, why is this possible? And why is it different from Feynman diagrams? Why couldn't we do this with Feynman diagrams? After all, they also had some structure. Three graphs have some recursive structure. So why couldn't we do it with Feynman diagrams? The reason is that in Feynman diagrams, not all the lines are the same. So we have these thick lines. So if we chop the tree at any point here through an interior line, we find something that is not an amplitude. It's something that is called a current. So we cannot construct recursively the object by using amplitudes. We have to extend the universe of our objects to include things that are called currents. But in this picture, every single line is an amplitude. Sorry, not an amplitude, it's a particle. But I have to tell you how to glue them together. But it turns out to be trivial in these new variables, lambdas and lambda tildes. You just identify the lambda tildes and identify up to assign the lambdas. Of course, the choice is yours, and that gives you what this object looks like. Now we are ready to do some examples. So let's try the 4 particle example. Well, again, we choose 1 and 2 to be specials. We get this, on each side, we need a non-empty set. So for 4 particles, they have to be 3 particle amplitudes each, only 1 particle on each side. So this is all we got, only 2 terms. Well, it's a minor improvement compared to the 4 terms that we had for Feynman diagrams. Now, you would ask, why don't we have terms like this? But remember that the black vertices and the white vertices are imposing constraints on the lambdas and the lambda tildes. So it turns out that this one imposes a constraint that tells you that the lambda tilde of these 2 particles are proportional to each other, and in experiments that doesn't happen. So these terms are not there. So we went from 4 to 2, That seems good, but maybe we can do better when we go to 5 particles. So for 5 particles, the whole answer is given by 6 terms. So we have the same, I've chosen 1 and 2 to be special. So we have 6 terms that look like this, where one of the amplitudes that we're recursing here is a 4-particle amplitude. Now we can go back, remember our 4-particle amplitude, and stick it here, and we get 2 terms for every term to give us a total of 12 terms. So that also sounds pretty good. Now these diagrams that we get look very different from Feynman diagrams, and they have been given the name of on-shell diagrams. I hope the name is obvious to you now, right? The reason they are called on-shell is because all the lines you see in the diagram are particles, and they are on-shell particles. Okay? Now you would say, maybe you're cheating, because it could be that each one of these 12 terms is incredibly complicated and very, very long, and it matches or is even worse than the answer you gave me before. But it turns out that for particles of helicity plus or minus 1, which are exactly the particles that I showed you before for the LHC, for the Large Hadron Collider, each diagram corresponds to a very simple expression in terms of the Plucker coordinates of these Grassmannians. So this one corresponds to this one corresponds to this, so you get 12 terms of this form compared to this. Those 12 terms agree with this answer. Now, such a miraculous simplification was first found by Park and Taylor in 1986, but how to generalize it and what it meant had to wait until more mathematical developments were found. Okay? Very good. So we're ready to ask, well, you have all these on-shell diagrams appearing all over the place, so you'd ask, well, what's the mathematical structure underlying these diagrams? Okay? And that's the subject of our next topic. So to answer that question, we have to go back to the basics. Remember the 3-particle amplitudes. We found a nice way to interpret them as elements of some Grassmannian imposing constraints on the lambdas or the lambda tildes. So I'm going to concentrate on the lambda tildes only, and that's why I've written down the number of constraints that these matrices or that these vertices impose on the lambda tildes. So the same story could be done in parallel for the lambdas, but I'm going to choose to do it only on the lambda tildes. So every black vertex corresponds to 2 constraints on the data, and every white vertex corresponds to 1 constraint. Okay? So just with that information, we can go back to a general on-shell diagram and ask, well, how many constraints do we impose on this lambda tilde data? So for a given on-shell diagram that has some number of black and white vertices, the number of linear equations or the number of constraints that we are imposing on the data is given by 2 times the number of black vertices. I told you there had to be a 2. The number of white vertices imposes 1 constraint each. And there are some number of internal edges that could eat up some of these constraints. So we have to subtract the number of internal edges. And that total number, k, is an invariant of the diagram. It's a number that tells us the number of equations that we have to impose on the lambda tilde. And a number of, if you have k equations, k linear equations on some vector of object, we can represent it as a k by m matrix. And now that we have seen the appearance of Grassmannians, we would think that we want to identify this object as a point in the Grassmannian GKM. So each row here is a vector in Cn, and it defines a k-dimensional subspace of Cn. Okay? So for each on-shell diagram, we land on a particular point in the Grassmannian GKN. Actually, not a point, but what is called a cell in the Grassmannian. So what's the summary so far? So scattering amplitudes can be computed in terms of these on-shell diagrams. Each one of the diagrams corresponds to a cell in the Grassmannian, GKN, and defines a planar ordering. I didn't mention that before, but the way we construct them using the recursion relations naturally provide us with a planar ordering for these on-shell diagrams. And scattering amplitudes are therefore naturally broken into pieces classified by this number k. As you apply these recursion relations, you produce a suite of objects, of on-shell diagrams, which take k's with all values ranging from 2 to n minus 2, and a given planar order. Okay? So what I want you to remember from this slide is, of course, the k, that is very important, but moreover, the planar ordering. This is something that is going to be crucial next. And now we are getting closer to answering the question, what is the mathematical structure underlying these on-shell diagrams? So if you're a physicist and you have found all these miraculous things happening, it's the time when you ask yourself, well, shouldn't this be something that mathematicians have done, right? And then your job is to start searching and asking people around and start searching if somebody had done this. After all, we have this nice combinatorial structure living on one of the oldest manifolds ever, which is the Grassmannian. So certainly somebody must have studied that. Indeed, somebody did. So Postnikov, in 2006, had this paper on the archive. And after you find that paper, well, our first reaction was to be very excited. And just looking at the table of contents, you see many things that look very, very interesting. So first of all, there is a Grassmannian, check mark. Schubert cells, well, we also have them because the on-shell diagrams live on different cells. Plucker coordinates, these brackets for the lambdas and the lambda tildes, so we have them. This Metroid structure, well, we don't know what that is, so we move on. Totally non-negative Grassmannian, so no clue. So you keep going, you keep going. You say, this boundary measurement map, could this be related to the metric C that we need? And here there is something that finally clicks it. It says perfection through trivalency. That's something we can relate to, right? So it sounds like we're on the right track. Maybe these two things will appear. And finally, there are these Plavik networks. So where does the name come from? Well, it comes from planar bicolor things. Well, what else? They should be these on-shell diagrams. Now you find these other things, trips there, mutations, and decorated permutations, and all this. So in the rest of the talk, all I'm going to do is just to show you some of the pieces that we found in this treasure chest and how they relate to physics. Okay? The first step, let's discuss this mysterious object or this mysterious item called Metroid struct. Well, Metroid theory turns out to deal with linear relationships among vectors. So just take m vectors in Rn, in Rk. Okay? So now we are thinking about these objects as being column vectors. They are k-dimensional objects, and we have n of them. Okay. And it turns out that the list of all non-vanishing minors, so you take any subset of k of these objects and compute its determinant, okay? And you record whenever these things are 0 or non-zero, and that's all you record, okay? So you have to compute all of them, and the non-vanishing, which ones are non-vanishing, encodes all the information you need to determine the linear dependencies of these objects. Now it sounds easy, but when you go to a large number of particles, this is a very, very complicated problem. And the general theory, the general Metroid theory, is very complicated. But once a planar ordering is given, the problem can be restricted and tamed. So that sounds good, because we saw the planar orderings were appearing in our problem. So maybe there is a chance that we can use this. So it turns out that once you choose a planar ordering, you describe something that is called the positroid, introduced by Postnikov. And the idea is the following. Just arrange the vectors in a k by m matrix. Well, that's exactly what we do anyhow. And this arrangement naturally introduces an ordering. And restrict to vectors such that all minors, whenever you pick vectors in the ordering that respects the one that you chose or how they appear in the matrix, so you just choose k of them sequentially, while you can leave gaps, but you go from the beginning to the end, then those minors, those determinants, must all be non-negative. And if you do that, you get a subspace of the Grassmannian, which is called the non-negative Grassmannian. Okay? Very good. I mean, this all sounds exciting and very interesting, but could it be useful for physics? Well, it turns out that given an on-shell diagram, what we need to do calculations is a representative of this k by m matrix that tells us the information about the cell where our on-shell diagram lives. So could this positron give us such an information? Well, consider, for example, this case that appears for 6 particles. Okay? So how would you go and construct this 3 by 6 matrix? It looks complicated. And if you do the counting of k, as I showed you before, the number of black vertices is 5, white vertices is 5, and internal vertices is 12, you get that k is equal to 3. So we need a 3 by 6 matrix. How do we construct it? Well, it turns out that there is a technique for doing so. It's called perfect orientations and boundary measuring matrix. So indeed, that matrix was the matrix we were looking for. And it's fairly simple. All you do is to take every trivalent vertex and you imagine that all these on-shell lines, all these particle lines, imagine that they are pipes and you have water flowing through the pipes. And every white vertex is something where you have one pipe that serves as a source and 2 pipes that serves as sinks where water goes out. And for every black vertex, you have the opposite. You have 2 sinks, you have 2 sources and 1 sink. You assign labels to each of the vertices. And then what you do is the following. The representative, the matrix you want to construct, is given as follows. It's a matrix where the rows are going to be labeled by the sinks. And the columns contain everyone. So every time you have a source with a source, the rows are gonna be labeled by the sources. So every time you have a source with a source and they match, you give 1. And every time a source with a source don't match, you put a 0. And now the remaining variables are obtained by following the water flowing from the source to the sink and multiplying the values of these variables that we have attached to the edges. Okay? So here it looks trivial. There isn't much to show, so that's why I decided to show you another example, which is this one. So consider this example, which is more interesting. It's a 4-particle example. Here I've chosen 1 and 2 to be the sources and 3 and 4 to be the sinks. So clearly we get the identity matrix here. And let's see for the entry 1, 3, how we compute it. We start at 1 and make a trip along the graph until we reach the sink 3 and multiply all the values of the edges. So alpha 1 times alpha 5 times alpha 6 times alpha 3. Sometimes you have more than one way of getting there, from a source to a sink, and you are just supposed to add up over all possible ways of getting from a particular source to a sink, and that gives you the matrix. Now the theorem is that for any on-shell diagram in GKN, such an object admits one of these perfect orientations. And it's called a perfect orientation because the rules for how you orient the white and black vertices are given. So every white vertex has to have only one source, and every black vertex has to have 2 sources. Okay? So this construction solves our physics problem, how to construct this k by n representative. So it has become very, very useful. Now, in mathematics, these numbers have a name. You wouldn't be surprised to know that they are called edge variables. But given that these graphs are planar, you could also think, or you might be wondering, if we could do the same thing with faces. It turns out that it's also possible to construct phase variables and define the metrics in terms of phases by following some simple rules that connect these entries with products of the variables that we attach to each one of the phases. And the reason I'm introducing these phase variables is just to show you that there is going to be another branch of mathematics that appears into these on-shell diagrams that we didn't expect. But before we do that, let me show you a couple of, well, actually 3 curious identities, but I'm going to show you first 2 of them. And they are curious from the physics point of view. And they are the following. Remember these double black vertices. They are imposed in the constraint that all the lambda tildes are proportional to each other. So if that's the case, then in any on-shell diagram where you see 2 of these ones, you could also replace them by something that looks like this. After all, they will impose the same kind of conditions, because the condition that we see here is permutation invariant. So we could replace this by something like this. Likewise, any double white vertex, we could replace it by something like this. It turns out that these have names. These are called the merge and expand moves. So this will allow you to relate different on-shell diagrams that classify or contain the same physical information. In terms of mathematics, they give you the same cell in the Grassmannian. And the last one, the third one, is something that you get by applying this recursion relation in 2 different ways. You can compute the 4-particle amplitude by choosing 1 and 2 to be special. In that case, you get this diagram. Remember, the first one that I choose to be special is given by a white vertex, and the second one by a black vertex. Or by choosing 4 and 1 to be special. So if you turn your heads, you will see that here we have the same structure as here, but now with 4 and 1 replacing 1 and 2. And we get a different object. I didn't bother to draw for you the other planar orderings. Here I'm only choosing one particular planar ordering, and they have to agree. So the fact that this has to agree with this is somewhat surprising from the physics point of view. But it actually is something that appears in mathematics and is known as the square move. Now, I'll tell you why I introduced the phase variables before. It's only for the following purpose. Just to say that a very exciting area of mathematics known as cluster algebras actually makes an appearance in all this. It turns out that these phase variables that I introduced before form what are known as a seed of a cluster algebra. And the square move is what is known as a cluster transformation, also known as a mutation. So cluster algebras are this mathematical structure that has appeared in many areas of physics, and this is just one of them. So could it be that cluster algebras are a unifying principle, or could it be that they are like Fourier transforms that appear almost everywhere? So we will have to wait, and only time will tell us if there are connections among the different areas in physics where cluster algebras are appearing, or it's just a coincidence. But I couldn't also resist the temptation to mention that if you take these diagrams, which are planar, and you compute or you determine the dual graphs, now in terms not of variables, but as a graph, you look at the dual graph, you get something that are called quivers. And the mutation corresponds to an operation that physicists found, in particular Cyber found in the 90s, which is now known as a cyber duality. But this is yet a completely different area of physics. It has nothing to do with the scattering amplitudes. It has to do with actual theories. It has to do with theories that in which precisely you don't compute the scattering amplitudes, because these processes don't allow you to do it. So it's yet a different area of physics where this appears. Okay, so we have gone very far along the trip on Postnikov's paper. So where are we now? So we have gone through all this. We made it to mutations. So the last step here is something called decorated permutations. So why do I want to discuss this? Well, there is a secret agenda for why I want to do it. But for the time being, my excuse is to say that for a given scattering amplitude, we have to sum out all these on-shell diagrams. Now, drawing these diagrams is going to be a pain, especially if you want to write a paper, you want to draw all these diagrams. It would be extremely painful to draw all of them. So you want to find a more compact way of encoding the information of each one of these on-shell diagrams, of label them. If there is a nice way of label them, then you don't have to draw them. You just have to give the label. It turns out that there is such an efficient way of encoding the information, and it's given by a way of assigning a permutation to each one of the on-shell diagrams. Now, instead of thinking about the particles as being pipes, think about each particle line as being a two-way road that you can walk along. And every time you walk and hit a y vertex, you are instructed to turn left. And every time you walk along this path and you hit a black vertex, you are instructed to turn right. And if you do so, any on-shell diagram will induce a permutation. You will start somewhere, you choose any point to start, and you will end up somewhere else. So 1 goes to 3, 2 goes to 4 by the rule, 3 goes to 1, and 4 goes to 2. Now, in order to definitely classify these on-shell diagrams, you have to add a slight decoration to the permutation, which is given here, but that's not very important for our purposes. You can just see what we do is that if the permutation ends up in something that is smaller where you started, you keep it. If it's larger than the place you started, in the planar ordering, you keep it. If it's smaller, you add n to it. Okay. Very good. So now I can tell you the real reason I gave you these decorated permutations, and it's the following, is to promote a book that came from all this research. So this is a book that contains everything that I have explained and, of course, much more. And it's called The Grassmannian Geometry of Scattering Amplitudes. So in the final, so I know you think that this is the end of the talk, but it's not. Okay. So in the final 3 minutes, let me give you the conclusions of the first part and the second part of these lectures. So the standard approach for computing amplitudes uses Feynman diagrams that I told you. And each diagram mixes on-shell and off-shell information, depicted here by the fact that we have different kinds of lines. And what we now know is that on-shell diagrams provide a different way of doing this. And they also provide a fascinating connection between computations that are relevant for actual experiments and mathematics and recent mathematics. And not only that, they also provide an efficient tool for determining analytic formulas for these objects. So there are some pressing questions. What is special about these particular combinations of cells that compute amplitudes? And can this idea of positivity be turned into a fundamental principle of nature? And the reason I want to discuss this, or I pose these questions to you, is that there is some partial answer, known as the amplituhedron, introduced by Arkani Hamed and Trinka. And this is a partial answer to these 2 questions, and a great subject for another whole series of lectures. Thank you. Okay, I'll repeat the question. Okay, so the question was, every Feynman diagram that you saw was a tree diagram. Even though the on-shell diagrams have loops in them, they correspond to this linear combination of 3 diagrams. Now, in physics, we know that we are also supposed to sum over Feynman diagrams that contain loops in them. Question is, can this be generalized to the case when you have loops? So let me just go ahead a couple of slides. So here, I forgot to acknowledge the different agencies that give funding. But then, if we move on, I was planning to show you an example for 6 particles, but that's too complicated. But here is the answer to your question. So these are the ones that give the 3-level recursion relation. If you now allow these terms to be included, where you now merge 2 particles into each other, then you get something that computes for you all loops in this theory. So in the lecture today, I only concentrated on this part, but once you add this part, you also get control over loops. Very good question.
Are there any extensions to massive theories as well?
Yes, so recently there's been an extension to massive theories. Yeah, I didn't add the reference, but I can give it to you afterwards.
Is it easy to heuristically understand how does an extension work?
Well, the extension, basically a massive particle, very roughly speaking, can be thought of as the entanglement of two massless particles. So if you know what to do with one massless particle, now you have two of them, and you think about this massive particle as this entangled version of these two guys, right? So, but by no means the story is completely understood, and it's not at the level of being able to draw these on-shell diagrams, finding what the Grassmannian structure, if any, is there, is still an open problem. So this is a clear invitation to anyone who wants to jump into this. It's the case of massive particles is wide open. In fact, a massive particle can be thought of as a massless particle in higher dimensions. So you can start asking, can we go to higher dimensions and repeat all this story and then compactify? Yep. Yes.
So this is all done in Minkowski space-time. Is there, but one might be interested in quantum field theory and curved space-time. Is there a way to isolate what the flatness of the metric, where the flatness of the metric is playing a role here, so that you introduce curvature in the metric, something is going to get complicated or get difficult? Or
yeah, so tomorrow I'll introduce a different formulation, which is what I call the geometric formulation, in which we're going to describe the same scattering amplitudes, but from a different perspective that allows you to think about this as a novel kind of a string theory that is called ambitwistor theory. And this one can be put on any background metric. Well, and people have done some of them. So it's still work in progress, but the story tomorrow can be described as is embedded in a more flexible background.